All right, y'all. I'm going to walk through the different calculations and graphs I want you to do just in case you didn't all sink in from class, which is totally reasonable. Hopefully this video won't be too long, but actually it shouldn't be there. Um, too much there. All right, so this is the kind of data you should have gotten. You should have gotten a distance for with 3 or 5 repeats of the first distance, and then 7 other trials. And you should have a distance and a time. So, if you remember today, we talked about how that the equation for acceleration for this is going to be displacement is equal to, right, 0.5 times a times t squared. And we can rearrange that to be that the acceleration 2 times acceleration, or 2 times displacement equals divided by time squared equals acceleration. So I'm going to use that. I want to find the acceleration to be in this box here. So I'm going to put in 2 times the displacement, so equals 2 times the displacement, and I click on the distance here, because that's basically displacement. I know I'm losing a negative sign, but that's okay. Divided by t to the second. I got to click on the time to the second. And then if I want that to propagate down, I click here and I drag. Okay. So now I have my acceleration for each of these. Alright, so now I want to make my graph. So I want to graph acceleration versus distance. Now, it's a little bit tricky. So a couple things we need to keep in mind. First of all, when we're doing this, I don't want my repeated trial. So I'm actually going to, I probably should have done this to begin with. I'm going to pull out the repeated trials. I'm going to copy this. We will need this later, but I'm just going to put it off to the side over here. And then I'm going to delete this information just so I have a little bit less clutter here. Okay. You could start. You could just do that to start. Like, there's no. It might be easier to do it to start. And notice I used the first trial. I didn't use the best trial. I used the first trial. It turns out maybe it actually, in this case, it is the best trial. But you want to use the first trial so you're not biased. Use the first trial of everything else. Use the first trial here. Okay. So I want to graph distance versus time acceleration. Okay. So I can do this. Highlight it. Highlight it. This is slightly different from the method I think I talked about today, but it works. Insert chart. And that's not the chart we want. That's okay. We go here. We go to scatter. There we go. You're going to have to click B as labels. Okay. That means it's going to graph distance down here, and then it's going to graph acceleration up here. I actually don't particularly like having a title there, so I would actually delete that. But you're going to want to add axes titles. But anyways, first, so we go to customize. So chart title, no, but I definitely want axes titles. So horizontal axis is height in meters. Actually, I'll probably say height meters. And then the vertical axis here is going to be acceleration in meters per second squared. Okay. All right. So you got that. Oops, I lost it. Customize. Here's what you need to add to this. You're going to want to go to series. Scroll down. Check trend line. Make sure it says linear there. If it doesn't say linear, we got a problem. Under labels, choose use equation. That will probably not be relevant in most of your most labs, but it could be in some. So I'm going to ask you to do it anyways. And then you check R squared. That's what matters. This R squared is really low. That's good. That means that these two variables are unlikely to be very related. In other words, height does not affect acceleration. That's kind of what we wanted to show. Okay. So we've got our graph. All right, and you're just going to copy that graph into your data, or into your lab report. Okay. All right. The next thing we have to do is we have to figure out a z-score. If this R squared is really high, you don't want to do a z-score at all, or do anything with standard deviation. But because it's low, we can do something with standard deviation. So I go back to here, and I want to do it with acceleration. So I do equals average. That's going to average, and I highlight everything above it. Okay. Hit enter. There's my average. 10.27. That's not too bad. And I also want the standard deviation. Okay. So I'm going to highlight all of that again. Make sure you do not highlight your average as well. Okay. And then you want what's called the z-score. Okay. The z-score is a measure of how many standard deviations you are from your expectations. So our expected value is 9.8. I want to know how many standard deviations we are away from that. So what I'm going to do is I'm going to say, okay, how far apart are my average and expected values? So subtract them, then I divide it by the standard deviation. If this value is less than 2, your data agrees expectations. Okay? If it's more than 2, it doesn't. Let's just hope that you get less than 2. Okay? And the reason why that you do it this way is because standard deviation is a measure of precision. And so we're saying how accurate we are, knowing based on our precision, which is not very good in this case because we're doing it with like hand timing, how accurate were we? And the answer is we were actually pretty accurate if you consider that as a percentage of our precision. Precision was bad and our accuracy was okay. That means actually, given that our precision was bad, we were actually pretty close. Okay. All right. The second thing you want to do, or the next thing you want to do, so we got that. That's our z-score. The next thing we want to do is we want to look at our error. Okay. So our coefficient of variance is a measure of how much our results varied. So we want to sit there and we want to say that is equal to the standard deviation divided by the average. And the reason we do that is so it's like kind of a percent. So this is like on average, our results were like 27% different. That's pretty big, but actually not surprising given our timing. So then we look at our time. And that's why we do our repeated values. All right. I want to look at this and I say, what's my biggest and what's my smallest? 0.4. Oh, actually, I need my average. So what is my average of this? Average of my times? It is 0.51. Cool. The biggest minus my smallest is 0.6 minus 0.4. So I do 0.16 divided by my average. And it's telling me that like based on that, my variance, my sort of expected variance here is about 0.31. Okay. So on so like I have a 31% kind of error expected, possible error in my measurement. And I got about a 27% variance in my results. That means that like, this measurement being that bad is like, totally reasonable and could explain the error I'm seeing in my results. Now you notice I didn't do this with the height measurement. I could have done it with the height measurement, but it's gonna be really small. Anyone can see that like these values change by a lot more than these values. All right, so we only want to do it for the one that has more error. If they're similar, which is not great, but if they're similar, you might have to do it with both of them. But in this, usually it will be timing will be the biggest error by far. Okay, so that's how you do the set up the equations and create the graph and calculate all this stuff. All right.